Hey guys, Junkie the Monkey here. Today we're going to talk about binary. But before we can talk about binary, we need to understand what it is we know and how that translates into binary. We're not going to spend a whole lot of time talking about what we're going to be talking about, so let's just go ahead and jump into it. So when we count by one. So we say 1, 2, 3, 4, 5, 6, 7, 8, all the way up to 9. But when we get to 9, something really interesting happens. Now, these are called counting numbers. And we often omit one of them that is relatively important. And the one that we always omit is 0. So, if we look at our number system here, something interesting happens here after 9. So, essentially, we have 10 possible values before we have to expand into another digit. That gives us a pretty good base to go on, and it's interesting that I use the word base there because our number system is based on a system of tens. When we multiply something by a power of 10, we increase the amount of digits. So a shorthand that oftentimes teachers tell is if you're multiplying or if you're adding 10 or if you're multiplying by a power of 10, then you just add a 0. So if we have 10 times 10, we'll say that the answer is 100. If we have 137 and we multiply this by 10, then what we're doing is we're adding a 0, so our value would be 1,370. The reason that this is the case is because once we've gotten past 9 in any one digit, we now have to expand into another digit. That's another place, as some people call it. Now, the reason that this is really interesting is because when we're talking about our number system and why binary was used as the number system for computers, which we discussed in the last video, we look at the fact this is called binary and this is called base 10. And I'm sure that at some point in your life, somebody has told you that you use a base 10 number system. Binary, hence, the word bi there should give it away, but binary means 2. And so, if this is base 10 and it has values ranging from 0 to 9 before having to roll over into another digit, then binary, meaning 2, has 2 potential values. So, instead of having 0 to 9, we'd have 0 and 1. Those are the only possible values in a digit before we have to roll over into the next digit. So, if we had a number in binary, this is digit 1, right? This is the least significant digit. In 137, by the way, it's the same. The 7 is the least significant digit. In this binary number, least significant digit is this, and this value can have a value of either 0 or 1. There are no more values in binary. It's 0 or 1. If this thing is filled and we want to add another value, say we want to add a 1 to this, well, there's not room here because there are only 2 possible values, and so we have to roll over into the next digit. The reason that this is important, that whole rolling methodology, is because this is what tells us what the values are going to be. So, if we look at just an example, let's say that we have the value 120. Okay, say that for whatever reason we want to convert this number to binary. We need to explain kind of a shorthand for how to convert to binary. So if this value here is the least significant digit, the first digit in a binary sequence we can say is the same as 2 to the power of 0. Okay. Can be either a 0 or a 1. This value here would be 2 to the value of 1. This value here would be 2 to the power of 2. This value here would be 2 to the power of 3. And what am I meaning when I say this? Because this can be kind of confusing, right? Well, 2 to the power of 0 is 1. 2 to the power of 1 is 2. 2 to the power of 2 is 4. 2 to the power of 3 is 8. And so what we get is, in this scenario, let's say that we have the number really quick, and then we'll get back to our 120 number here. So if we have this, that means that this value here is 0, right? So we're not adding 1. But this value here is set. It has a value, right? This is 2 to the power of 1, so we add 2. So the number 0010 is 2, as we see down here. Now, I'm going to leave all of this up here for now, but here in a minute we're going to go ahead and erase this. So if you want any of this information to this point, make sure that you copy it down. Okay, so what did I do here? We didn't have a value here, we did have a value here, so in this case, this was pretty simple, right? Because we just had a value here and nothing else. Well, what about if we have values in different pieces here? So like, for instance, let's say that we have the binary sequence 1010. How do we get that converted into a base 10 number? Well, the way that we do that is we take the value here, which is 2 to the 0. It's not set, so this is going to be a 0, right? Plus the value here, this is 2 to the power of 1, which is 2, and this is set. So we're going to go ahead and say 2. Then we go to the third place. We say this is 2 to the value of 2, and it's not set, so we'll go ahead and add a 0. And then we go to the last place here, and this value is set, so we say, okay, 2 to the value of 3 is 8, and this is our conversion. So when we take all of these things and we add them together, what we got is 10. So 1010 has a base 10 value of 10. Awesome. So that's honestly as simple as it is. It gets really, really a bad rap, and it's really, really portrayed as this massively complicated thing, and you're kind of judged oftentimes by laymen as somebody that, if you understand computers, they're like, oh, and he knows binary, when in fact it's actually not a very complicated thing. So let's take our example here. So we want to convert 120 to binary. So we just converted a value from binary to base 10, but now we want to convert a base 10 value to binary. How do we go about doing that? So converting from base 2 to base 10 is pretty simple. Converting from base 10 to base 2 is a little bit more complicated. And so what we're going to do is we're going to create a small little table here of values that we can use to make this a little bit simpler. So 2 to the value of 0 is 1, 2 to the value of 1 is 2, 2 to the value of 2 is 4, 2 to the value of 3 is 8, 2 to the value of 4 16. 2 to the value of 5 is 32. To the value of 6, 64. 2 to the value of 7 is 128. So, and it goes up by 2. If you notice here, we're multiplying by 2 each time. And so the next value would be much higher, so on and so forth. So, now that we've done that, we have our little table here. So, let's go about converting this. And there are a couple different ways to do it, but there's a really, really simple way. The really simple way is that we start with the highest value of 2 that goes into the number that we're trying to convert. In this particular case, it's 2 to the power of 6. Now, 64 goes into 120 how many times? Well, it goes in once. So we'll just put a 1 here. Then we take a step down and we say, okay, how many times does 32 go into the remainder of this? Right? So we have 120 minus 64. What does that give us? The answer is 56. So we have 56 remaining. And now we take a step down. So we just did 2 to the power of 6. The next step would be 32. How many times does 32 go into 56? Well, it goes in one time. So we put our 1 here. And then we say, okay, what is the remainder? And the answer is 20. The remainder is 24. Okay. The next step is 16. How many times does 16 go into 24? The answer is 1 time. So we subtract 16. Give you a second here to figure this out. And the answer is 8. Okay. Then we take a step down and we say 2 to the power of 3 is 8. How many times does 8 go into 8? Well, it goes in 1 time. And then we continue down to the other values. Now we have 0. How many times does 4 go into 0? Well, the answer is 0. How many times does 2 to the power of 1 or 2 go into 0? The answer is 0. And how many times does 2 to the power of 0 or 1 go into 0? The answer is 0. And so, if we want the value for 120 as binary, the answer is 111000. And that's the easiest way that I've found to do this conversion, and it's pretty simple. Now, it gets a little bit more complicated as you increase the value of your base 10 number, but so it becomes a little tedious, but it's pretty simple. It's pretty straightforward. Cool. So that is, in essence, how to convert values from numeric values from base 10, what we're used to base 2, which is binary. Alright, so let's go ahead and erase everything. So, now that we've talked about how to do numeric conversions, now your question is probably something along the lines of, yes, but we don't only store numeric values. So how does the computer take the ability to store numeric values and turn that into something meaningful to people? And that question becomes really interesting when you look at computer systems and how they're doing what they're doing. So numeric values are pretty straightforward. It directly relates to a set of ones and zeros. That is intuitive and it makes total sense. But what about if we want to store a string? And what I mean by a string, we'll talk much more about this later, but what I mean by a string is something like this. Hey there, junkies! So this set of letters here doesn't really directly reflect anything in binary because they're not numeric. So how do we store these types of things in a computer system that is only numeric? It's only ones and zeros. The answer is that some really smart people got together and decided that because we interact with a base 10 system, the only real values that we need at any given time are 0 to 9. So we can represent everything that we need to do in numeric terms with values ranging from 0 to 9. And what they came up with is something called the Ascii system. And the Ascii system is basically a conversion set, and we'll just show it here, of numeric values as well as letter values, because the only thing that we really need is 0 to 9 to be able to represent something numerically in a format that we understand. The rest of the values are dictated by these numeric values here, represented and correlated to a set of alphanumeric values. A, B, C, all of the letters of the English alphabet, but even in addition to that, they also reference things like punctuation, periods, commas, semicolons, exclamation points, parentheses. And all of these values are really, from a textual standpoint, all we need to know in order to construct basically anything that we could possibly think about from a textual perspective. So we'll go ahead and pull this off screen here for just a minute. And if that's the case, then we can start really trying to convert our little string here. And we'll just pull this off to the side so that it makes it easier and minimize some of this other stuff. If I can for how to do that. We'll get there, guys. There we go. So now we can easily convert our little string here into something that is represented effectively by a computer system. So we'll just go over to our little chart here, and we'll say the value for H is 0, 0. Oops, that's incorrect. Look at me making mistakes already. 0, 1, 0, 0. 1, 0, 0, 0. And this as a whole represents the value H. Now, that's a really long number, right? For a lot of digits to represent one character. And this leads into something that we'll talk about later. But each number or each series of binary, what we call bits, has to be combined together to create some of these textual occurrences. And strings in general are quite expensive from a computer's perspective, as you can probably tell. So we would go through this chart and we would take each of our values and we would put them in side by side to create that string, which is really just a collection of characters. That's important to keep in mind. And that would represent our string, hey there, junkies. But now we've mentioned a couple things here that we probably should spend a little bit of time talking about. And also, it's interesting to point out that notice that these things are grouped in fours. Now, there are a number of reasons for that. And some of them aren't exactly intuitive, but we're gonna take a stab at a piece of it right now. So we need to talk about a digit, and each one of these digits in this binary number has a name. Now, that name is something that you've probably heard about, but never really understood what it was. Okay, So take just a minute here. Oops. And we're going to erase this. And let's look at some values for binary. So 1, 0, 0, 0. Okay. So each one of these digits, as I was saying, has a name, and each digit is called a bit. Now, this is important to realize and understand once we get into computer systems, as a set of bits equates to some value in your software application. Now, how do computer systems organize these things? Because we don't want to constantly keep track of each one of these bits individually. And the answer is, typically in computer systems, not typically, always in computer systems, a bit is not something that you interact with regularly. What you do interact with is something called a byte. And a byte is a collection of 8 bits. 8 bits combined to make a byte. And I'm sure that you've heard of byte before. You've heard of bytes, you've heard of kilobytes and megabytes when referencing networking bandwidth and things like that. You've also probably heard about the amount of storage that you have on your cell phone or your tablet or your computer being referred to in gigabytes. This is a very, very common term even amongst lay people. How do we reference that back to something relevant to what we need to know? Well, the answer is that we actually need to understand operations in computer systems in order to really refer to what binary numbers mean in a computer system and how we interact with it. So, in the next video, we will talk about elementary operations in computer systems, and in that talk, we'll talk about things that you can do with those bits and bytes. I appreciate you guys watching. Thank you very much for tuning in. Make sure that you like and subscribe below so that you can be notified whenever new videos are posted. I'm so glad that you guys are joining in on this journey of learning computer systems and how to write software. Thank you very much for joining, and again, we'll see you next time.